All right, guys, let's get started. Okay, so today I'm going to talk about a couple of things. The two challenges that are coming up, which are the CIFAR competition and then the term project, right? So those are the last two things left, and then of course a final exam. All right, so today my goal is to go over the CIFAR-10 challenge. So I'm going to start giving you the code for that. We're going to start building, setting the rules. There's rules to this competition, as there would be for any competition, right? So we're going to go over that. We're going to use the GPU, of course, today because we can't do 10th class classification with CIFAR-10 and a deep neural network. So I'll go over all of that. So we'll go into GPU Scholar. Let me get the GPU and just kind of do this later in class because we won't be able to all get a GPU in class. It doesn't work that way. All right. So I'll go over that. I will also go over, that's what I'll do today. Just start going over that code. However, I do want to go over just the project, the specifications and the CIFAR-10 specifications in general. My goal is to finish the CIFAR-10 example, and then also next week to do an example of how to deploy a PyTorch model with Onyx on GitHub. And then I think I've given you everything, like the basic stuff for you to do both the competition and the project. So the rest of the semester will be just me like going into very specific things about neural networks, just kind of, like the background and foundations, but you'll have everything basically to at least get started. Does that make sense? All right, so I'm gonna begin, I guess, with the project. So let's somewhere. So the project, of course, is not due until the end of the semester. All right, so you will do a presentation the week before finals. Okay, so that should be the main idea. All right, so I've written here a few rules for the term project. Apply your machine learning knowledge to solve a problem of your choosing, and it must be approved by the instructor. So you need to let me know the problem that you're trying to solve. In the past, for whatever reason, students have always gravitated towards sports prediction. I have no idea why, but this happens a lot. They want to predict teams and things like that. I'm sure it's not about gambling. And then so you will select a topic, get some data. You don't have to annotate the data, you can get it. I'm sure there's a lot of data out there. Train and test a model. In general, it would most likely be a classification or a regression. Somebody asked me, for instance, can I do a prediction of stocks? My answer to that is yes, but it's not going to work. And if you want it to work, then no, because we haven't covered that topic. Sequential machine learning is an involved topic, time series data and RNNs in general. Yeah, Henry.
So we use stochastic processes.
I mean, you use stochastic in everything for the optimization, but I just mean the way that you map the data is different, very different. All right, so definitely don't do anything that's sequential like that. So if you like stock price predictions, where you obviously it makes sense to know the price of the stock in the previous weeks and months to predict what it's going to be in the future. That's something else, right? Another class called sequential machine learning. Spend a whole semester. All right, so definitely not projects like that. Instead, it's just going to be like classification, regression with no time dynamics or time components. Okay. All right. In PyTorch only. Okay, so I stress this. This course is in PyTorch. If you show up with Keras or something, I'll know you just copied this off the internet. Okay, so PyTorch only. You must deploy on GitHub with Onyx. So make sure that you realize that that needs to happen. It has to be an application, right, that does something. Obviously, I will show you how to do this. This will be a lot easier than the PyScript one because the coding is just JavaScript and the model does all the heavy lifting. Okay, so but I need to demo that, and my plan is to do that next week. You will need to demo, do a presentation, and submit a report with your findings. So you understand that idea. Groups of 2, I think, because 3, then one person just doesn't do work that much. So let's keep it at groups of 2. I know some of you, most of you, or some of you are cybersecurity students. So if you have a if you want to do a cybersecurity project, you can go to this link, and there's several data sets there on intrusion detection, phishing, IoT, malware, I think. So you can check that out if you want. Or, as I said, you can collect your own data. So you're not limited to this, but, I wanted to give you that option. As I said, it could be sports, just run it by me. Start thinking about it now and try to have some ideas by next Thursday, okay? Because keep in mind, we only have about 3 weeks left. And so you have that project and the challenge, the competition. So that's the challenge. I'll give you the data, obviously, because it's a competition, and I'll give you the code, but I'll give you code that if you run it, you're not going to win. You'll get a B, right? Because you just did that. But if you're a B student, then yeah, just do that. All right. But your goal would be to win, right? So that's kind of my, and actually there's a good motivation for doing a competition, because it really lets you understand why you need to learn all these other things. You want to win, normalize the data. Otherwise you won't win. Those kinds of things. Okay. Does that make sense? Are there any questions about the project before I move on? Nope. All right, great. So you can find the description there. I think I put the dates there. This one is definitely during the week before finals. I'm not sure about the timing for the competition. It just depends. There's no rush, but at the same time, we can't do a thing of some people present now and other people continue presenting. It's got to be on a day, right? And whoever gets the highest that day wins, right? So, but there's no rush, okay? But I don't know exactly. I think I gave you a date, and I'm just not sure if if I'm gonna postpone it a little. All right, so the project can be found here on the projects and surveys, and then if we scroll down now, CIFAR-10. Okay, so I will basically give you, as I said, the data set today, how to use the GPU Scholar today. I'll start creating the code for the thing that really is usually the thing that, where you have trouble, which is the data, right? So usually, you don't know how to convert it into a tensor, so we'll do that today. And then after that, we'll start adding that to a neural network, okay? So that's basically the idea. We'll go over that. I'm just going to say something. Yeah, so I put the dates there for CIFAR-10. Okay, so I'm going to click on this. All right, so here's the rules for CIFAR-10 as well. Using the CIFAR-10 data, but it's got to be the data that I'm going to provide, okay? I've already have a train set and a test set, and the evaluation is going to be based on that test set. Does that make sense? So it's going to be there. Or if I decide to modify it or something like that, but I have to give you some. All right, rules, PyTorch only. And that no keras, no TensorFlow, no Hugging Face transformers, no FastAI or similar libraries, no ChatGPT or, it's got to be from scratch. You do it. Yeah, go ahead.
What's a Hugging Face transformer?
What's a Hugging Face transformer? Hugging Face is a company out in Silicon Valley, I guess. And they created a library called Transformers, and it allows you to use transformers.
Sounds like an algorithm.
Yeah, Hugging Face is a company. But it's a very important ecosystem. So it's FastAI. So these are, and that actually, it goes with some of the hints that I will give you to win. Okay, but there's rules. You can see the rule is no Hugging Face transformers. So, or FastAI. What do they provide? They provide something called transfer learning, which you may not know what that is, but they do make it available. So I'm saying don't use that. However, if you notice, I didn't say don't use PyTorch native transfer learning. So you can use that, but I'm not going to show you. That's outside of the scope of the class, but it's a competition, right? And what I'm trying to show you is that you'll throw whatever you can to win. Okay. I will say, and as I said, I will describe what transfer learning is at some point. I will provide some of the recommendations. For instance, another tech, even though I'm not going to cover it in this class, really the algorithm that's the best deep learning algorithm for image classification is something called the CNN, convolutional neural networks. Again, I'm not providing that, right? But if you want to win, maybe that's something that you would do. Do you see where I'm going with this? So I will do the very basic deep learning algorithm. It'll have several layers, it'll be proper and have everything, and we will achieve a score. However, I know some of the tricks that get you a little bit higher and higher, okay? And so definitely, if you do this on a laptop, I mean, you're gonna lose. All right, so that's guaranteed. All right, so anyway, that's some of the rules. So definitely, as I said, PyTorch only. Basically, from my code, you need to build up, okay? And no Keras, no TensorFlow, no Hugging Face transformers, no fast AI or similar libraries. Train and test a PyTorch model from scratch using the CIFAR-10 code that we'll start building today. You will need to show all relevant performance metrics. The F measure will be in general the metric that we're going to focus on the test set. Okay, whoever gets the highest F measure on that test set for the 10 class problem wins the competition. Got it? Yeah. Now you don't have to do it in real time. I trust you guys. So, you know, so you can, if you achieve it, just have a report or something that you did it. And believe me, the other students will question if they don't see something that looks accurate. Okay, got it? All right, so here I created this little, and like I said, I didn't write them down, but I will give you some of the hints of how to win. Like I said, transfer learning, CNNs, definitely batch normalization, maybe deeper neural networks. You know, you got to try lots of architectures. This is your opportunity to play with everything that's available. I created this little link here. Yeah, it went there. Okay. So I created that link, and it takes you to basically the course repo, Machine Learning Foundations, under homework. So you can, if you're navigating, you can click on homework. So there's the generative KNN. Here's the challenge. So here's the data set, okay? It's on GitHub. It's not my data set. Somebody put it together about 5 years ago, but I have selected this one to use. So this has the actual images, okay? So these are the CIFAR-10 images. So what do we need to know about CIFAR-10? There's a train and a test set. The train set should have 50,000 images. The test set should have 10,000 images. There's 10 classes, and they're like, you'll see like car, boat, bird, horse, I think, something like that. And they're color images. The images are 32 by 32, so they're kind of small. And you will see that even though they're small, we'll need a GPU for this. Got it? Does that make sense? Yeah, Henry.
And you're holding the test set.
It's right here. So it's like I said, you should do your training on the train set and evaluate that model on the test set. I trust that you guys will do that. You see what I'm saying? You don't have to, it's not like you have to come to the competition. I'll give you a data set and you apply your model there. I'm not that crazy. All right. So it's just you guys do. Somebody could cheat, yeah, but don't.
I mean, like, what would be cheat? Like for example, like what you can do.
Cheating would be not following the rules of the competition. Your model should be trained on the train set and then evaluated on the test set. And whoever gets the highest F1 on the test set wins the competition.
But how do you prevent from overfitting your test set?
You'll never train your model on the test. Your model,
I guess what I'm saying is that like once you test your test set, right? You see, oh, it has this score. I'm gonna run it again with this tweak. And I got this score. I'm gonna choose this model over that.
Yeah, which score? Run it 10 times and average it. And I trust that's
Or if I guess what I'm saying is that like
it'll be what I can tell you, it's if you're at 65 and you run it 10 times on that test set, it's always going to be around 65. You're not going to have a 65 and then a 99.
Well, I guess like when you tweak your algorithm to fit your test, to fit the test set.
The train, no, you should never show the test set to your model.
No, don't show you test it, but like once it, like, I don't know, say you trained your test set, not test set, you trained your model using trained data.
Yes.
With X parameters or something like that. And you test it, and you've got a mediocre F1 measure.
Okay. Yes.
Then go back, change parameters of your model again,
Yes.
and then you get assigned a higher score. And
Yes.
you thought, hey, I want to choose this. Like, wouldn't that be overfitting the test set?
It's not overfitting because the weights were never adjusted by looking at the test set. Yes, you perform better, and that's fine.
I guess I'm.
The weights, as long as the weights are not adjusted by looking at the test set, you're fine.
Okay.
You can try 100 iterations on the train set and every time evaluate on the test set. That's fine. I'm not keeping that a secret. I just want to know, think of it this way. I just want to know what's the best architecture to solve this problem. Whoever gets that best architecture gets the best score and therefore wins.
Okay.
Does that make sense?
Yeah.
Yeah. So did everyone, that's a very important question, right? So never, you can show your model the test set for evaluation. And it'll be in my code also. I will do this. So you guys can just follow along, but it should only be done on the trains. It should only, the updates to the weights should only be based on the trains. Yeah, all right.
And sorry.
Huh?
Can you swap around, like, you're probably gonna have it hold to like constant number or something.
Oh,
You
what?
just like for the shuffling.
In the
Right.
train set, yes, the test set should never be given to the model for training. No.
Okay.
So you can only
You
do
can't
training on the trains.
You can't change your test set at all?
Yeah, you can do another split. Like you can take train and test, combine it, randomize it, split it again.
Okay.
You should only, that's the rule. That's
Okay.
actually a very hard rule of the competition.
Okay.
Yeah, it's think of it as you're gonna win $1 million. I would hold out the test set secret. And then yeah, during the competition, I make it available and in real time, but I mean, I'm giving you a pre-printed lion. You know? So anyway, so did that make sense, guys? And I will give you the code. We're going to start doing the code today. Okay, got it? All right. So you can see the train set here on GitHub. It's a airplane, and then you can click on the images, and it should be like a little airplane. They're very small, but they are color images, which means it's RGB. So you have that additional thing. They're 32 by 32. Do the math there. That's like over 1,000, right? Okay. So we're going to start doing this. So how do you get this data set? So it's actually pretty easy. Oh, sorry. CIFAR-10. So all you have to do is on GitHub, click on this green button here, right? And it'll download zip. Do you guys see that? So you will download a zip file to your downloads on your local machine. Everyone with me? All right. So that's what you will do to get the data set. Then, of course, now because this is going to require a lot of compute, as they call it, we need to use GPU Scholar. All right. So this part, again, don't follow along here because let me get a GPU for sure. So we're going to start that. So, and then today's script is this one. So CIFAR-10 challenge is not complete at this point, but it basically is to load the data, which is actually probably the hardest part. Okay. So let's go ahead and get started. So I need to go back to Brightspace. Here we are. All right, so we go back to Brightspace, and now I'm going to show you how to access GPU Scholar the way that I know how to. I'm going to give you some recommendations and everything on how to use it and how to load your data, how to create a Jupyter notebook and everything. All right, so if you remember, you go to this module, GPU Scholar, click on that. You open this Word document here. Okay, and then you can scroll down, and there's a link in there that we're going to use. You need to be logged in to your Brightspace. Double check that you still have access to this. You should all have access. Okay. Should be this one. Copy that. right? So this should take me to right space. All right, here we are. So this is the GPU Scholar. Again, don't get a GPU yet. So what I usually do is I go here to this button, Interactive Apps, click on that, and I select Jupyter Notebook, okay? So I click on that, and then this is where you can select the GPU. So the amount of time you get is 2 hours, which I believe for CIFAR-10 should be enough, okay, for training. If it wasn't for whatever reason, save a checkpoint, and then in the next 2-hour cycle, read in the checkpoint and continue training. You can do that with PyTorch. Okay, so GPU, it's 2 hours. This is the description of it. First available, although you can select, you know, if you want one of these specifically. I usually uncheck these two. And so I click launch. So then it starts the process of queuing your GPU. All right, so it's currently starting. Okay, here we go. So I got this blue button, connect to Jupyter. So now and it says my time, I have 1 hour and 59 minutes. So I'm gonna hit connect to Jupyter. And there we go. This is my environment. You should have something similar to this. So then I usually just go to desktop, and this is where all my information lives. Now, I also like to use I click on this thing called cluster here and Scholar shell access. So I like a little terminal, right? So this is where your 372 comes in, right? Your Linux knowledge becomes useful, right? So here, you know, we're going to have command line, and this will give us a little bit of more power to do certain things that we might want to do. So I'm going to navigate to desktop. And clear, so I have a whole bunch of files in here. So there's 2 spaces that are provided to you by the university. One is this default space for your desktop, and then there's something called Scratch. So if I remember correctly, it is Scratch something and then your username. I'll confirm that. Yeah.
There's also a an environment variable, I believe, $scratch. That'll show you your Scratch folder.
Okay, all right, great. And the great thing about that is it's 1 terabyte. So the only thing is it's not permanent. I think after 2-3 months, they have a policy that they clean everything out. But, you know, if you're doing a really big job, like 20 gigs at a time with big models, you have 1 terabyte of space for Scratch. But this one, I think, is only 25 megabytes. So if gigs. So I'm going to do my quota, which is a Scholar command, and you can see that it prints out how much space I have in my environment. So I'm currently at 20 gigs out of 25 for my home or Calix desktop or my user, but I also have in my Scratch Scholar, and then your user. That's what it is. In my Scratch Scholar, I'm only using 21 gigabytes out of 1 terabyte. So I'm only using 2%. So you can leverage that if you have really big things. Okay, that should be more than enough, I think. All right, does that make sense? All right, so you can use this for removing things also. You know, you do a RM, you know, RM something, right? And you can delete the files as you learn in 372. All right, so now let's go ahead and get into the environment. So every now and then I might reference that my quota. I've already done one part, so I'm not going to do it live, but I'm going to describe it. So if you remember, what I said is that you go to this link for the data, right? And you can go to this person, Young Kim, and just click on the code and download the zip, right? And that's going to give you a zip file, okay? With the train and test set. So here then, under desktop, what you would do is to load that data on here, you click on upload. Do you guys see that? So you click upload, and then it opens this up. and then you select the zip file that you want to do, and then there's going to give you like a dialog where you say upload. Does that make sense? And it is that easy to load your data set. So at that point, the data set will be in that space that I just showed you of your username, desktop, etc. on GPU Scholar. So you can see, I think I probably left in here or I deleted it. Do you guys see a zip file in it? Yeah, there it is. CIFAR-10 images master.zip. So that's the zip file that I uploaded to Scholar, okay? Now we need to unzip it so that we can use it. So that's where we go back to the shell. And so now I'm going to do ls-l. And you guys see I just write the red one, right? Master.zip. So all you need to do is unzip command and then CIFAR. I've already done this, so I don't really want to do it again. But when you hit enter, it'll unzip everything. And it creates this blue folder, CIFAR-10 images master. Does that make sense? And that's it. Your data is now at this point on the GPU Scholar, and you can start working on it. It'll now, if you want to know where it's located, remember 372 Pwd home, and then it gives you the path for you on your desktop. Any questions? Yeah, Henry.
You guys said the scratch thing works. Maybe echo capital.
The scratch thing works.
I mean, like the $sign.
Do you want me to act that variable? You mean? What's the command that you want me to type?
I don't know, like echo, then $sign, all caps scratch. Never mind.
I mean, if I do my quota, it shows me the full path. That's right. I know where it is. It's just that scratch Scholar and then your user. That's it. That's the path. Because I use this all the time. So I like it because if you want to save checkpoints, for instance, and things like it starts to become big really quick. The data set is very small, like 50 megabytes, I think. So it's actually not that big of a deal. But as you build more complex models to win, keep in mind those models do get bigger. And if you start saving a lot of checkpoints, you might see a little bit of an impact. Yeah, Henry.
Can you do print env type rep?
Hold on. Print
In
lowercase.
One word, printing.
Oh, print env.
Yeah. Space rep typing, so like a
Yeah, grep pipe.
pipe rep, sorry.
Oh, pipe.
Space, and then you do all caps scratch. Okay, so it's RCAC scratch. Sorry, my bad.
Oh, the variable is RC. Yeah, but you can see it's scratch Scholar and your user. Yeah. Oh, thank you. That's well, RCAC. And why is there a cluster?
Maybe it's like legacy.
Oh, legacy. Okay.
Something like that.
Got it.
Like on Anvil, it's just scratch.
Okay, great. All right. But anyway, we did the unzip, right? We did the unzip. So now you guys know how to unzip it. So do ls-l. You have your CIFAR-10 images master then, so you can cd CIFAR-10 master, ls-l, and you can see you got your train and test set right there, those blue folders, and then you can go into those and you'll find your images, okay? Got it? There should be about 10 classes in there, so you can go into the train, ls-l, you can see the folders per class. So this is a common thing in machine learning. When you want to do classification, you have pictures of airplanes, put them in the folder called airplane, and that's the class. And then you have pictures of boats, put them in a folder called boats, and that's the class. Do you guys see that? I like using that approach a lot because it's very easy. I can collect a whole bunch of images, just dump them. They're in the same class, and then my code just reads that as the labels. Okay? All right, so that's the approach I'm taking in this example. So this is important. Yes, please.
Then you need to put them all in one file eventually to train them out.
In one file.
Or in one data set.
You need to put them in one torch tensor. Yep. And that's what we will do. Yep. Good question. Got it? All right, so let's go ahead and I think we're ready to get started. I have my folder available, so I can start writing the code for this, okay? So I'm going to clear. All right, so that I'm gonna exit out of this one. All right, so now we go back to the Jupyter Notebook environment as we know it. Okay. I have the data set here, CIFAR trained data set, so I know that's there in my current working directory. Now I'm going to click new, and I'm doing this all kind of like to show you how this pipeline works. So I have a whole bunch of environments. I don't know what environments you guys have. I assume at least 3.7 and 3.8. I don't know if anyone's logged in where you can see the environment in under new. Nobody? All right. But anyway, that's an important thing, I guess, for you guys to tell me what environment it shows. You will be installing libraries in this environment, okay? So I'll be using 3.8 for this, so keep that in mind. Okay, so Python 3.8. Got it? All right, so now, as you can see, we are at the very familiar Anaconda Jupyter Notebook. You know, nothing has changed, but we are running this on the GPU. I will at some point, I have some code somewhere, I'm sure, that I can show you the GPU version. Something. All right, so I'm gonna write this one in, I'm gonna call this in class, and I will, it's the thing that I'll be updating through the lectures. So I want to have some, so I know, keep track of where I am. So in class, CIFAR-10 challenge, okay? So basically you should use this code for the challenge, okay? But take it from where I leave it to win. You know, you need to do all the tweaks. All right, so in class CIFAR-10 challenge, I've renamed it. I'm going to invoke my own repo. I'm going to show you where the code will live for, yeah.
What would be the, like, what would be, like you said, oh, the highest F measure possible or whatnot?
Yes.
What would be a good F measure?
If I tell you, then I don't want to tell you because I know like where I've gotten and how I've gotten to it. But
I guess like the ballpark, is it like between like 0 and 1 or something like that? Or like what are we looking at?
F measure is yeah, it goes up to 100%, right? Like in the Weka.
Oh, so it goes up to 100% up.
It goes up to 100%. Remember the Weka challenge or the first homework mini project, right? In Weka, what was F measure? 78, 80, 99.
Right, so, okay. And your goal is basically get to as close to 100 as possible.
Yeah, you win by getting the highest, yeah.
Right.
And nobody can get 100.
That's all I need to know.
Yeah, exactly. So, oh yeah,
Is any, I just, silly question, but has any student beaten your F score?
well, it's not that they've beaten mine. I mean, yes, oh yeah, my knowledge of the highest that I can get is from students.
Oh.
Like in the I do this competition every year, and I know what they have done very skillfully to win. They do simple little tricks, sneaky. But I don't. If I tell you, then it's no fun.
I guess
I would rob you. I'd be robbing you from the fun of all those hours.
Right.
So
I guess the only reason I was asking like the upper bound. I wasn't like I was wondering, I was just at the back of my head I was like, okay, F measure.
yeah, but because then you know, what if you get higher than
Right,
what I've been able?
What if it's like it goes from like 0 to infinity or something?
It doesn't go to.
Right, no,
It's an F measure, Henry. So you got up to 100. Got it?
Yeah.
Yeah. All right, great. So the one thing I was going to say, so MNIST, for instance, is the handwritten digits. It's in grayscale, not color, and you can get 98% accuracy on it because it's just handwritten digits. It's a 3, it's a 5, it's a 7. But this is much more difficult because this is an airplane, a bird, a car, a dog. You see that? So it's a much more difficult data set, but much more interesting. All right. All right, so let's start. So the code is here. Usually I'll put the code here in the repo under CIFAR-10 challenge. So at some point you might see more scripts arrive here. But currently this is the one that I will be using, and we're going to start building up from here. So the first thing I'm going to do is copy the libraries. Okay, so I'm going to copy the libraries here. I've already installed all these libraries, so they're available for mine. If you guys need to install something, you can just do pip install, for instance, Torch Vision. If you don't have it, you run this command, just hit the cell, let it install the program, and once it's installed, just go ahead and comment it out. Does that make sense? But that's how you can install some of these libraries. Probably image.io, I don't think will be installed. Torch Vision may be installed when you install Torch. Questions about that? All right, so let's go ahead and run the libraries. Oh, sorry, I think takes a minute the first time around. Okay, it finished. Good, because good GPU. All right. Now let's actually, I have some code for looking at the GPU. So let me open another. I'll show you. I don't know if I did this with you guys before, but click on this one. So in here, I'm sure I have. Trying to think where I have this. Oh, here it is. All right, this is what I was looking for. So these are some commands that you can run to get information about if you need to convince yourself that you are in fact using a GPU on Scholar. Okay, so you can go over here and do this. So Torch CUDA is available. True. What is CUDA? CUDA, oh, you want to answer? Yeah, go ahead.
It's just like NVIDIA's, like, not framework, but I guess like, library for dealing with GPU. Right?
Yeah, the firmware, right? Yeah, exactly. So NVIDIA created the C, C++, set of libraries, etc. Remember, the underlying is a hardware. It's a chip, a GPU, big GPU thing, right? And NVIDIA created this firmware and this library for machine learning, right? And that's the CUDA library, basically. So we're checking that we have it available. Okay, so that's something interesting to look at. How many GPUs we have.
Like the number of GPUs, like the, when you request it.
So I know that it looks like that, but if you try it, it actually only lets you select one. However, I have been told by Henry and other people that we can get multiple GPUs. It's just, there's another process, but Henry.
With like, you'll have to work with the Slurm directly,
Yeah.
internal and whatnot. But other thing too, is if you request more than one GPU, you're gonna wait longer, and you're gonna like. So like, say if you like, yeah, if you're just wait longer, much longer to get what you want or whatnot.
Yeah.
So it may not be worth it in some cases. I don't know how.
We don't need it for CIFAR-10, so don't worry about it. But it's something, believe me, we are working on this, and the program will have that at some point, but yeah. Okay, but you don't need it for 365 for sure. All right, so, you know, if you want to know the device number, like if you have multiple devices, you have 0 and 1. And, you know, so here it's ID 0. We want to know probably what GPU we have. So that should be this one. So CUDA. So we want to ask Torch CUDA to give us the get device name for ID 0, and it tells us that we have a Tesla V100, and that's, or an A30 or something like that. Okay, but this effectively tells you that you have indeed a GPU. Make sense? Yeah, Henry.
And is there just the index per GPU you have? Say if you had like 3 GPUs or something.
It would probably be 0, 1, and 2.
Okay.
Exactly. All right, so now we are ready to get started with, you know, I think at this point everybody can follow this video and you can get a GPU, establish an environment, which is very familiar, Anaconda Jupyter notebooks, okay? And then you can check that you got a GPU here. So now we can proceed with the actual code. It's this one over here. So, what do we need? We need to get the data. I'm going to close this one. Yeah. So we need to, so let's start, CIFAR-10 data, which you already uploaded as a zip file, unzipped, and now it lives in your desktop in the Scholar cloud. So then, cell, markdown, CIFAR-10. Okay. Full V. All right. So I'm gonna add a few more cells here. All right. So I'm gonna run this. All I did here is provide the two paths that I want. Remember, this is very important. You should only use the train set to train the model. I will even show you how, whenever you're dealing with the test set, you need to write special code to indicate, this is test code, do not update the model. Okay. So you'd be cheating if you do that. Yeah.
Wouldn't also be like, probably repeating over question, but wouldn't also be cheating if you say if you made a decision based off.
Yeah, decision of which model to use based on the test set. Yeah, but we're going with that because we just don't have time to do it in real time.
But normally you
It would be much more complicated. Yeah. Yes, I would put it in everyone would get a flash drive or something of the test set, plug it in and do the live demo, but that's too much effort. I trust you guys. It's just a little project. Not $1 million.
I don't know if that's a good idea.
Yeah. All right. Anyway, so these are the paths. So mine is home. This will be your username that you have at Purdue, the desktop, and then CIFAR-10 images, train and test. Okay. So these are the full paths that we're going to do. So I just defined them here. I'm going to hit run. All right. So the next process is the thing that, you had, the issues you had were with getting the conditions, for the KNN averaging, right? You were stuck in how to get the data from the images and creating the labels and all of that. We have to do that again. All right. But this time around, I'm showing you this approach. Okay. So let's go ahead here. All right. So again, the link is right there. Same link I provided before. All right. So now let's start with the train data. So this part is just going to be for the train data. Okay. The goal is to create a torch tensor of this. Remember that there's always lots of different ways of doing something. This is just one approach. Okay. All right. So the first thing I'm going to do is really not that complex. But the first thing I'm going to do is create these lists. So now I'm just going to type this up slowly. I kind of want to describe this very slowly. All right. So we're going to need 3 lists. So I'm going to call one list data set train. And then the other one is going to be labels train. And then the other one is going to be targets. Okay, so we're just going to do some lists initially. We're going to read the data from the folders, right? We have to iterate through them and everything, the process. Okay, so the path that I'm going to use is raw data train because I'm only doing this for the train set. So I'm going to use OS list to get the folders in there. So I'm going to do for folder in os.list directory, where the directory is going to be raw data train. Okay. So I'm going to print out. This is what you should always be doing when you're generating problems like this. Don't just copy a whole bunch of code and expect it to work, right? Line by line, print it, right? So that I kind of want to do this exercise with you guys. So print folder, that's the first thing, right? So if I'm getting a list of folders, print them. All right, so I'm going to go ahead and do that. See, since I'm specifically grabbing the train set, it's giving me the 10 folders for the 10 classes. So the CIFAR-10 has dog, horse, airplane, automobile, ship, truck, frog, bird, deer, and cat. This is the challenge. Okay, this is actually very similar to the 2012 ImageNet competition. This is the moment that changed, you know, that brought deep learning into the world, that made, you know, the huge impact. And so it's basically they were doing a competition very similar to that, to this one. They were using, I think, 1.1 million images, which was considered a lot back then, right? Anyway, so that's kind of what I did. I just printed the folders, okay? And then each folder contains certain images. So now we're going to proceed. Now within each folder, we're going to start grabbing the images, okay? So now I want to grab the images, and each image, I need to convert into a tensor, get the label and everything. Okay, so I'm going to do for image in os.list directory. Okay, and then I'm going to say os.path.join, and I'm going to join here the folder and the path. So I'm going to say raw data underscore train, comma, folder. Do you see that? So this is basically what it's going to give us the different images for every single one of the folders. So I grab dog, grab all the images of dog, and I know that it's from folder dog, so I have the label. Then I move to the next folder, airplane, grab all the images from airplane, and I know that the folder is airplane, so that's the label. You guys see that? All right, that's the key, a key thing to understand here. Okay, colon. Now I'm going to do, okay, so if folder, not in, I'm going to create a list of the folders just because I'm seeing them for the first time. So as I'm iterating through this, you know, I grab an airplane folder for the first time, I add it to a list. I see it again, I don't add it. Then once I see a new folder like dog, I add it to the list. And I'm going to end up with a list of 10 of these 10 folders, 10 words. So if folder not in labels train, I'm going to add it to the list labels train, basically. Labels train. And that to do that, you just do append. This code actually was written by student, you know, Joey Shapiro, James Higley. All right, so now, so labels train append, and now I'm going to add the folder. All right, so that's basically it. Next step is now we just do that kind of to have the folders in a list, but the next step is really to create the labels, right? So the labels are actually going to go in the list called targets underscore train. So now I'm going to do targets for this image. Remember, I just grabbed an image and I'm going to need to keep track of, I'm going to put that image in a list, and in another corresponding list, I'm going to put the label. So I'm going to say targets train dot append. Okay. And what do we append? We need to append the folder, but we actually want an ID. We want a number, right? Like which we can use the index, for instance, here, right? So in the list, first one is 0, the next one is 1, the next one is 2, and so on. So this is a very easy way to do that. From labels train, I'm going to extract the index. So I'm just going to say labels train dot index, And which index do I want? The index of the folder. Okay, and that should give me the number that I need, you know, for that image, basically. Any questions? All right, seems like everyone gets it. All right, so that's basically that part. Now I want to process the image. I'm going to use a library called image input output, which is you saw at the very top to read the image. Okay, so let's go ahead and do that. So I'm going to say img r. So this will give us a NumPy array. And so I'm going to use the image io dot imread function, okay, so that I can read in this image. So here I need to now use OS path join again to put together the whole path efficiently. So I'm going to say os dot path dot join dot oh yeah, and then provide the parameters. So it's going to be raw data train, right? That's the path, folder, and the actual image. Do you guys see that? And that basically puts together the full path. And then we want to tell it the pill mode. It says pill image. So it's going to be pill mode equal RGB. So remember, we're going to be using color images here. Make sense? All right. So now that this is done, oops, we should have a NumPy array. So here you could do things like resize, crop, etc. But this is CIFAR-10. So at least, you know, everything's just the same size. So everything is going to be 32 by 32 by 3. All right, so there's no need to resize or crop, but usually this is where you would add that type of code if you had like images that are different sizes, etc. All right, so now we can proceed to convert the NumPy array image R into a PyTorch tensor. So I'm just going to do, oops, I'm going to do new line, img torch dot from NumPy. And I'm going to do image. Does that make sense? Converting it to Torch. Now you do have to do something else in Torch. Torch likes images to be channel, height, and width. Usually we get height and width channel, right? That's how we get them, like 32 by 32 by 3. But Torch wants them to be 3 by 32 by 32. You guys see that? It's just a thing that Torch likes. This is actually why I like Torch, because it's got these things, you know, consistency are nice. All right, so there's a very easy way to do this. You just use a function called permute. All right, and then basically think of it this way. 0, 1, 2, right? So that would be height, width, channel. But we don't want that. We want channel, height, width. So basically then we just move the 2 here. And that's it. You guys understand? Yeah, go ahead.
So the 0 and the 1 represent the height of the.
Yes,
Okay, and that's like pixel, or is that?
it's the dimension.
Okay, and then the 2. I mean,
It's the 3, the RGB.
So it'd be like maybe B here or R or G.
No, it's both, all 3 are there.
Oh, okay, okay. Oh, okay, 0, okay.
Yeah. So remember, it's like X, Y, and then Z in that direction. So you have an image, another image, but then RGB.
Okay.
Like stacking pieces of paper like that. Yeah, that's actually a good analogy. So X, Y, but then R, G, B. You guys see that? So yeah, go ahead.
You probably already answered this.
Yeah.
Probably just now. What does permute mean?
Permute is just switching things around in the dimensions.
Oh, so you're just swapping.
I'm swapping the channel. Yeah, so it's, so okay, let me write it like this. So that's why
It's like transform, I guess.
it's exactly a transformation. So I have 32 by 32 by 3. That's how NumPy gives me the image, because that's how it comes. But PyTorch does not like that. PyTorch likes this.
Gotcha.
And so we just denote that this is 0, 1, and 2. By using the function permute, we're able to convert it to this by just doing 2, 0, 1.
This is just flipping the rows and columns on itself.
Flipping the dimensions.
Oh, yeah.
Got it?
Yeah.
Yep. No, good. Yeah. I want you to understand. So you'll just do this, okay? And then, again, it's a torch thing that it wants. Then the next step is to convert these images to float, just to make sure it's a float type. I can't remember the data type here. It might be float 64, it might be float 32. This is important. Float 64 is bigger, means slower training. Okay, bigger files, all that. This is an area called serialization, sparsity, all that's, making efficient deep learning models. So I think in another example, I want to say I showed you how to go from float 64 to float 32, I believe. Yeah. So that may be helpful to you if it's taking up too long to train. Yeah.
For trading the
Precision,
precision.
a little bit. I don't think for this one it matters, like going from 64 to 32. But certainly if you went from float 32 to integer 8,
Right.
you know what I mean? You're giving up some performance for sure. Yeah, but that's important. That's a thing you guys, as the world moves on, will need to become experts at as well. All right, that's just because the models are too big. So anyway, so here I'm just doing a basic float, okay? All right, so now that we have this, we can normalize the data, and a quick way to try to do that is just image equal 255, basically divide everything by 255, right? And that should give you numbers that are like decimal. Yeah, exactly. Make sense? 0 to 1. So it's a normalization. This is not the only normalization, but I think I've mentioned many times normalization. Neural networks like normalization. There's going to be another technique called batch normalization. You may need that to win CIFAR-10, okay? But I'll show you that technique later. All right? So anyway, now that we've done this, we can go ahead and add the image to the dataset train list. So I'm going to do dataset train dot append. And I'm going to add to it IMG. Does that make sense? So if we do this, it takes a little bit, but we should be done. So let me actually go from here. Make sure that you always, whenever you're repeating this, that you clear out those lists, because otherwise you're just going to keep adding to the list. Okay. So, right, so if there are no errors, this should run. Okay, there we go. It's running. It's running a little bit slow because it's actually reading each image from the hard disk. As you know, that's an expensive operation. It's running, right? Yeah. So it should start. Oh, I guess I forgot to print these folders. That's why it's. But anyway, yeah. Yeah, Aiden.
Is the GPU supposed to help with stuff like this too?
No, it doesn't help that much here. Yeah, that's a good question, actually.
It's all next to IO, not necessarily HL.
Yeah, this is just reading from the hard drive. Yeah, so I wouldn't. I mean, there's more memory and things like that, but in the training, definitely.
Right, it's internal.
I encourage you actually to try to train this on your laptop. I do.
Take a while.
Just do it. Huh? Well, of course, if you have a GPU that's CUDA enabled and you're using it, you're good. Yeah, it's got to be a special GPU. Not every GPU will work. It's got to be only certain GPUs with certain, because yeah, all computers have some kind of graphics processing unit, but it's got to be those that are supported. Yeah.
So my Sandy Bridge CPU from 2012, with like 4 cores, is it gonna work?
Oh, it'll work. Just gonna have to wait for yourself.
Yeah. I'm not
It would
even.
be faster just do one for all.
All right, it finished, right? So now let's go ahead and print labels train. So see our data and what we have in there. So labels underscore train. All right, so we've got these. We want to keep track of what the labels are. Now something very important. We want to measure how many samples we have, right? This is critical. So we have len of targets train. I'm just doing it by the labels. Could have done it by the images. Targets train. It's train. Around that one. So as I said, there's 50,000. You can see there 50,000 samples for training. Yeah, go ahead.
So I've been like, I guess following along, and when I do.
You already solved it.
Yeah, when I do the len target strength, I get a 49,976.
49,900.
Yeah.
900.
And 76. I'm missing 24 bonus.
I mean, I've done this twice today, so I don't know. I always got,
Still, it should-
I did 50, I got 50,000 every time. Did you use, you can follow use my code that I have on here?
That's what I.
Oh, you're using that? And you're sure you're reading from train?
Yeah.
I'm not sure why you would be missing 24. Unless like somehow mysteriously that zip file was updated since when I got it, but I got it this morning. So.
I thought it was like 5 years ago. But
It was, but I got a copy of it this morning. For to load here.
I'll just try to read that.
What I can't, yeah, try. It could have corrupted, is possible. At the end of the day, I don't think that 24 would make such a big difference on your training. To be honest, but just 24 out of 50,000. But I don't know. It's
Oh,
hard.
it's not something worse.
I would try it on another computer, on another experiment, and see if all of you tell me that you're getting different. Yeah, I don't know. We'll have to look into it. Sorry. Yeah, try it. Henry can probably show you some commands on how to count it on Linux,
Actually, you can do that.
but not right now, Henry. Let me finish. But you can definitely show him how to do some pure Linux commands. All right, so let's keep going. So, because I really do want to make sure you guys understand this part, as I think this is where you're going to get stuck. And so I'm trying to make this very clear. All right, so what do we know? We know that there's 50,000 in there, right? So now let's start inspecting them individually. So remember, right now, the targets are in a list and the images are in a list. So the images should be in the dataset train list, right? So I'm going to do dataset train. And I'm just going to use indexing, as you guys know, number 3, for instance. And I just want to check out the shapes of it and the data type. So if I click on it, it's a torch tensor and it's 3 by 32 by 32. Do you guys see that? Great, that's your image. Yeah, Henry.
And train's just like a list of those, right?
Currently, it's a list. Currently, I have a list of tensors, torch tensors, which are the images. And each one is 3 by 32 by 32. Okay? All right. So you can try other ones. They're basically the same. We'll view one of these images in a sec. Okay? Yeah.
Here's the question.
Yeah.
Would a matrix be a 2-dimensional tensor?
Would a matrix? Yeah, that's actually not a stupid. That's actually a tensor is just could be 3-dimensional, hyperdimensional. Yeah, even a scalar. All right, so now I've printed the length of all the train set and also one image from there. Now we need to convert that list of tensors into a torch tensor. Okay, you guys have used this command before, so probably shut down. Let's just give it a minute. All right, so we should be back. All right, so we are back. So now, like I said, I'm going to take that list of tensors and I'm going to create it into just one single tensor. Okay, so I'm gonna do data train. And that I'm going to call torch dot stack. And this function can take a list of tensors and just stack them. And now we're just going to have a single tensor instead of a list. Okay. This is very useful. I may later choose to create a data loader. And if I do that, I'm going to take another approach. But it's kind of nice to just have everything in a nice little neat little torch tensor. Yeah.
So we're just gonna have one tensor of size 50,000 by 3 by 32 by 32.
You'll see that in a second. All right, so now I'm gonna do, I need to provide the list. So that's data set train. And I'm also going to do that for the targets, the labels, right? So I'm gonna do targets underscore train. And that's going to be torch dot tensor basically. So torch dot tensor should do it. So we will provide to it targets underscore train. Okay. Now, one thing that we want to change for this one is the data type, because these are labels. We want to convert them to an integer type of thing. So we're going to use long. So I'm going to say here dot type. And we're going to typecast it to torch dot long tensor. Like that. Okay. So now let's go ahead and print the shapes. Yeah. Do you have a question?
Yeah, long is, you mean by long as in like compared to floats or integers?
Yeah, this is an integer basically. The long integer. All right. So now another thing that you can do is you want to get into the habit of saving things in when you do this machine learning. Think of it this way, right? So you're using GPUs, you're using the Scholar cloud, you only get 2 hours. What if you're training and you run out of the 2 hours, right? Or you want to save something. So we're going to get into this habit, if you will, of saving. Okay, so currently I only have a data set, but Torch has a way of saving data sets even. All right, so I'm going to do torch dot save. Okay. And we're going to save the following. So we're going to provide like a tuple of 3 things. So we're going to say data train, comma, targets train, and also the list of labels. So labels train. So it's going to save it as a tuple of 3 things, basically. Labels train. So now that I have these 3 items, I just need to provide the name, and this should be saved in the file system of Scholar. So I'm going to say something like in class CIFAR data. Okay, so that you guys can see it. So now you can run, and then also, although I'm not going to load this one, I'm going to provide us a comment. If you want to reload it from, you would say something like data 1, targets 1, labels 1. And you will use torch.load. Okay, and you obviously you need to specify the name, so it's going to be in class CIFAR-10 data. Does that make sense, guys? Basically saving the data to the hard drive, and then later on, tomorrow or whatever, you just load it again. And it goes back to the state that it was in. So I'm going to go ahead and do that. It's processing, done. Now I'm going to go to the file system, and I should have something called in class CIFAR-10. So I can go to my shell. So I'm going to do clear ls. And there it is. No. This one, right? Yeah, there it is. Okay, does that make sense? And so when you start training your models, one of the nice things of Torch is you can save a checkpoint, what is called a checkpoint. So train every 30 minutes, save a check. And then you can always just continue training from there and so on. All right, so that,
More efficient.
are they pickled files? That's a good question. It's its own native to Torch. They're serialized, very efficient.
Gotcha.
Yeah, it's its own thing.
And when you have like a model that you train, you want to test or something later on, can you just dump
You want to
it?
monetize the model? Did you say that?
No, I mean, say you have a model you want to save,
Yeah,
you just like dump it the same way.
yeah,
So
that's,
without a tuple, like you just have like.
yeah, exactly. You just model dot save and it'll save it as a PyTorch thing.
Okay.
And then later on you do model dot load and or torch dot load into a model.
Gotcha.
And yeah, it's easy. It's easy. But those are called checkpoints. You probably want to put like the date, the time, whatever it is. And you know, they can get big if you're saving a lot of them. It just depends on what you're doing. All right, so you guys saw that I saved it. So we can go back to the code now. At this time, it's probably a good idea to go back here to Scholar and check how much time we have left. So you can see I still have an hour and 9 minutes of this. Okay, this is important. Save your file. And that's also another thing, like the Jupyter lives outside of that. So if you save it, exit, you come back with a new one, your file is still there and you can just use it. You can see all my, you know, I have a lot of files. Right? Yeah.
Just a courtesy note, when you're done with your session. And you still have like an hour left or something, just end it. pretty
Oh,
early.
yeah. I'll
Because
do,
it's basically, you're renting, not renting, but you're. Basically saying, hey, I'm using this GPU right
Yeah.
now, and other people can't. use
yeah,
it.
exactly.
If you have a very long queuing time,
No, you're right.
yes.
So you just click delete, yeah. Yeah, he's right. So you're taking away someone else's chance to use a GPU. So
Basically, it'll take longer for them, so the queuing thing, although it's like very quick in this case, or sometimes it won't be as quick. And to speed up to other people, when you're done with your session, terminate it. Like I just tell Flora, I'm like, oh, someone else can use this resource now.
great. All right, so now I've created from the list of image tensors, the actual tensor, right? So that's in data train. So I want to print the shape yet again. So I'm going to go ahead and do, and this was the question you had asked. So shape, so I'm going to hit run. And as you can see, it is now a torch tensor of 50,000 by 3 by 32 by 32. And so we have our data. That's nice to have. Once you have your data like this, you can go ahead and, you know, start building your neural network basically. Okay. Although, and you could load it directly into the neural net, or as we saw in one previous example, you can create a data loader, which makes your life a lot easier. All right, so now let's print the shape for the targets. So I'm gonna do targets dot targets train dot shape. Right, and this should be 50,000 as well. But it's a torch object, and we have basically here our labels. Okay, if we just want to look at one of these 50,000 from the torch tensor, you know, how do we do that? So this is very easy. You just grab data train. And let's say I want 4. The fourth picture, exactly.
Or the fifth picture.
Yes, the fifth, yeah, exactly, the fifth picture, exactly, good. And if I do dot shape, what's the shape going to be?
3 by 32 by 30.
Yep, exactly right.
But basically the same thing as before you stacked it. The only difference is it's now a tensor instead of a list. of
Yeah,
tensors.
that's what changed, but once we get it out of the stack, it's basically what it was, yeah.
Like it would be like this, it'd be like it's more efficient, but like if you were to mimic that with a list, you would just do the length of the list. Then you would do the shape of each tensor or whatnot, right?
Sure. But it's better to have it like that. I mean, it's just a convenient thing.
Plus would it add more like checking? So like say, for example, if one of your with listing be like anything, right? In Python, right? So like you have like a tensor with different shapes.
Mm.
If you stack it, would it be like an additional check, like, hey, all these have the same, these tensors?
Yeah, they need to be the same size
Okay.
for you to be able to stack.
That's another reason to stack your tensors so that you
For
would,
a check, I mean, you should watch, you actually should pay attention to this very closely and do it yourself.
my Canon project, one of the images.
Don't you know, it's not Copilot or something. Don't expect it to do it for you. It's kind of, you have to do.
The, I don't know, like one of like the projects like Canon thing,
Mm-hmm.
one of my images, I don't know which one, but it had a different. I'm not sure if it's RGB, it's not RGB or some other thing, like third dimension or something like that.
Yep.
And it kept like throwing it off, so
Yep.
every time I had sufficiently high K or something, we just crashed. the code.
Yeah, I remember that.
I was going insane with it.
That's a very common machine learning problem.
Yeah, but like I would like, if we were to stack it or something, you would know, hey, actually, oh, one.
Well, I would just print the shapes, you know, like I like printing shapes. All right, so we looked at this. We'll look at the image in a bit. That's another thing, just, you know. We also want to look at the labels. So I'm going to do target underscore train. And I'm going to just pick, you know, this has 50,000. So I'm going to pick from 34,000 to the next 1,000. So 35,000, right? Hit run. Targets maybe. Yeah. All right, hit run. And you can see those are the sixes basically. Does that make sense? 6 class, yeah.
Oh, 6, okay, so it's the 6th class.
Yeah, or 7. Because it starts at 0.
Oh, yeah.
So yeah, so if all right, so that's actually a good one. So if I do like that, right? What number are you gonna get?
10.
Zeros
Oh,
at the beginning. All right, now I'm gonna do from 14,000 to 15,000. What am I gonna get? What number? 2 maybe. I would be a good guess. Yeah, nice. If I go to from 24 to 25, 4. You see,
you should probably shuffle it, right?
huh? Yes. So that's actually where I'm going with this. So they are currently not shuffled. Do you guys understand that? There's a, you know, what if the model only looks at the 3s, 4s, and 5s and doesn't look at the other ones for some reason? That's not good. So the solution to this is to randomize it. Okay. So you can either randomize it from scratch, or if we create a data loader, the data loader takes care of that. And that's a really important thing to do. All right. So we saw an example of using a data loader this week, I believe, or no, last week. And then I'll show you how to do it here as well. Does that make sense, guys? All right, great. So we looked at the labels. All right, the next thing we want to do is look at this tensor as an image. Okay, so we want to just see the images, right? So I want to print the images. Print images. You don't need to print the images to train the neural net, but it's nice to look at them, I think. So you guys already did some of this, right, for the KNN example, so you probably can write some code for that. I'm going to take one image, let's say this one, right? So take that. Take that. I don't need to shape anymore. I'm going to change it to maybe 14. So if and I'm going to say IMG torch. Okay. So if I do IMG torch, see, it's got the data. We want to look at the data. If you notice, it doesn't go from 0 to 255. It goes, it's decimal. So it was because it was divided by 255. That means it was normalized, right? All right. So now what can we do? We might want to use something like image pill to create the image, right? So let's say image, and we may need to make this torch into NumPy. Okay. IMG Okay, image is not defined, so from pill import image, right? Let's try that. Pill, I think, is a native library of Python, so it should be in there already. All right, so image functions right there. So now let's go ahead and try this one again. Okay, so I need to, what is it? Show maybe? Gonna have to check my own library. Or if you guys have the code, help me out a little. Be great. All right, so okay, so let's see. I printed this. Oh, I said, oh no, but this reads from a path. Let me try image open.
You have to convert to NumPy.
That's what I was about to try. So what was the command for that? To NumPy? Underscore? Or no underscore?
Yes.
I think Python everything.
All right, so let's try this one. Nope. Can't remember.
It
Must be paying.
Yeah.
I think it's torch.to NumPy, you have that as part of it, not as like a
Oh, torch. Yeah, I see what you're saying.
dot.
Yeah, yeah, yeah.
And that's a guess. I don't like it's.
No, that's a good one. So torch to NumPy, and then we would imgtr, right? Try that. Nope. You guys find that? That would be really great. Because I don't have that part off, that I can remember.
It's dot NumPy.
Dot NumPy. Is it the torch?
Yeah, it's tensor dot NumPy, which is what they named the variable. So it looks like you just take the image tr dot to NumPy, because they get the actual tensor link.
Yep. Try that. img. Oop. img tr NumPy. Okay, oops. And then that would be a NumPy, and then some image is probably some. All right, let me just Google it.
First one was 2 NumPy.
Image pill. Torch tensor to image. Right, so this should work. Okay, so we're gonna use torch vision for this one. So import torch vision dot transforms as t. Okay, so we're just gonna do that. So So load the library, that worked. Okay, great. Now we can go down here. And I'm going to do, I have a tensor. It's a color tensor, so I'm going to do transform. And I'm going to call T dot to pill image. Like that. Get that for now. Okay, that works. And now we will apply that transform. So I'm going to do img equal transform. And I'm going to give it the tensor. So in my case, I think it was img tr, right? I believe. Okay, that worked. And now I want to view it. So I'm going to do img dot show. About img. There we go. And it works. So tiny, but it's actually, what is it, a dog or something? Yeah. Hmm?
You know, that literal network to find out.
A dog on a leash? Really? Wow, you can. All right, let's try a few more images just to kind of get a feel for it. They're not shuffled, right? So if we want to see different ones, we got to like jump really high, right? So I'm gonna do 6,000. But you know, shuffling is important. So 6,000 or so. Okay. And this one is a horse. All right, that one's very obvious that it's a horse. All right, so that, yeah. All right, so let's do a few more. Let's jump to like 26,000. That is, it's a vehicle. Yeah, ice cream truck.
It looks like a dog.
Looks like a dog to you. So if it looks like a dog to you, imagine, you know, it was going to be much more difficult for an AI, right? All right, so that's, what is it, 26,000. Let's do two more, so 36,000. Bird, yeah. Bird, and then one last one. 46,000. And that one is a cat. So this is the CIFAR-10 challenge, okay, guys? So you have to train your model. I think there were 10 classes, I believe. That's actually a number. Let me confirm that. We can confirm that by looking at this list. Yeah, so there's 10 classes. Make sure you run this on the test set also, just to make sure that there's 10 classes in there. There should be, but make sure you double check. Yeah, so that's kind of where we are for now. So I've created this. Next Tuesday, I will continue with this code. The test set would be pretty much the same process, just use the other path, create all of that. On Tuesday, we're going to create the data loaders, right? Data loaders. And then we're going to build, I think we should be able to finish this code on Tuesday, create the neural network, a deep learning algorithm. If you want, go ahead and, I mean, you should be able to build this on your own at this point. You have all the code that you need. So start playing with it. And then we're just going to continue for the rest of the semester. I will give you hints until we get to the competition. Does that make sense? Yeah. Yeah, that's why I'm ending a little early so that you guys can present. Yeah. Any questions, guys? Yeah, Henry.
So for the basically we're done next Tuesday.
Yeah, you'll have
Everything will work. You just have to optimize it.
That's right. It's gonna be the same performance metrics function that we have already used.
Gotcha.
Like I have a little function and it prints out confusion matrix. That's what we're gonna use.
And if you won't.
So-
And use it, you will get, it will give you model and everything.
I will give you the model, yeah.
It won't be as efficient.
Exactly. I will do a model and I believe classification, F measure will be 62% or something.
And is our grade just the F measure we get?
Your grade is, if you get the score that I give you, you get a B. If you implement this. Or an F, probably. I don't know, but.
What? Hold on. Okay, I'm sorry. If we like.
I mean, you, obviously I can't do that. I mean, just do your best effort.
Right, I guess, but like.
It's more for fun for you to win. That's why I give you a trophy. That's what you get for winning. Okay? It's not dependent. Your grade is not dependent on the score that you get in the challenge.
Okay.
Got-
What if we got like a 0? Could we just like invert like out of the.
You can't get a 0 because I'm not gonna give you something that gets a 0. It's gonna get like 62 or. All right, guys. So, yeah, some of you still want to present. So, if you guys want to leave that are not presenting, you can, but you can also stay to look at the presentations of some of this is, we're getting at the last chance for you guys to present, right? Because, I can't spend too much time on this. So, but we're done with this. I'm going to stop the video here.